Hello and welcome to Schrodinger's classes. Today we'll be doing Pauli's exclusion principle and Hund's rule. Now the Pauli's exclusion principle states that the I'm having a minor glitch that the number of electrons that needs to be filled in various orbitals. In our previous video we have seen the Aufbau principle and how orbitals change from their grounded state to their excited state and in their increasing order. Okay, the number of electrons to be filled in various orbitals is restricted by the exclusion principle. Thus, the exclusion principle is nothing but a restrictive principle on the number of electrons that needs to be filled in each orbital. To say what it actually state or what Pauli had actually stated, it states that, I'll put this in quotes, no two electrons in an atom can have the same set of 4 quantum numbers, that is set of 4 quantum numbers. This was the exact phrase what Pauli had said in its exclusion principle. Now let us see an illustration of this principle. Let us take this as one of the orbitals, that is, let this be 1s square. Now always notice spin quantum number must always be different. In our later videos we'll be explaining why, because this I'm telling you a bit because this has some properties of magnetism, that is paramagnetism and diamagnetism, but let's save it for further chapters because we'll be studying that in detail. Therefore let first one be n equals to 1, I equals to 1, m equals to 0, and s equals to plus half, that is the spin, and over here n equals to 1, I is also equals to 1, m is equals to again 0, but the only thing that's different is the spin. That is, in each orbital there are 2 electrons with opposite spin to occupy this 1s square orbital. Now next comes Hund's rule of maximum multiplicity. From the definition it can be defined in a number of ways. Let us write all the definitions down. That is, number 1, in this rule electrons rather that is electrons prefer to occupy separate orbitals so that they have parallel spins. In the next definition, Hund's rule suggests that the number of unpaired electrons, let's write in the chemical form, the number of unpaired electrons in a given energy level is always maximum. Is maximum. And lastly, electrons occupy as many orbitals as possible of an incomplete subshell. Now for illustration, let us take nitrogen, which is 7. Thus the number is 1s squared, 2s squared, 2p3. Now let us take these two as the first and the second s orbital, and let this be px, py and pz. Therefore this is how the orbitals fill up in a nitrogen atom. Thus we have 2 fully filled 1s square orbital, a fully filled 2s square orbital, whereas a half filled p orbital. Now why do we study the Hund's rule? That is, we need to figure out what the importance of Hund's rule is. Let us list them down. It plays an important role, writing it in short, an important role in interpreting, as I already said this in this video, the paramagnetic as well as the diamagnetic characteristics amongst the transitional and the rare earth elements. And secondly, Hund's rule is of no significance in regard to the s subshell, as there is only one s orbital. It is however of considerable importance, that is, it is of importance when p, d and f subshells are considered, as it accounts for the presence of unpaired electrons.